Hi students, good morning. Today we are going to discuss the phasor diagrams of loaded alternators. So before going to phasor diagrams of different loaded, we will discuss some basic points, that is lead, lag and unity power factor. So already we came across in basic electrical engineering. There we studied regarding the resistance, inductor and the capacitor. We know unity power factor will be achieved by using of resistive load, and lagging power factor will be there in the inductive loads. Leading power factor will be there in the capacity loads. First, we will recall this basic concept. After that, we will go for how the steps to draw phasor diagram. After that, we will go clearly with the derivations, each phasor diagram of lagging, leading and unity power factor. So now we will go for from basic points. That basic point is the resistor. So we know in the resistor it carries the current and it have a voltage and there is a power factor, and that power factor is unity. Why? Because the angle between voltage and the current is 0 and the current is in phase with the voltage, so that the power factor is unity for the resistive loads. And for pure inductive loads, the current lags the voltage with an angle of 90 degrees. For pure capacitor, the current leads the voltage by 90 degrees. If it contains any internal resistance, then there is an angle of pi. So these are the basic concepts of resistor, capacitor and the inductor. So now we will discuss the steps to draw the phasor diagram. Okay. So in these alternators, basically we will take the reference as current, but normal phasor diagrams we will take reference as a voltage. So now we will discuss the steps for normal phasor diagram. So here I will draw, you will see. Okay. So in the normal first step in this normal phasor diagram, I am considering the voltage as a reference. So voltage as a reference, that is V. Okay. So if you consider it for lagging power factor, then the current lags the voltage with an angle of pi. So here the current lags the voltage with an angle of pi. So why? Because it is inductive load, it is not a pure inductive, so that here it is not 90 degrees. There it have a inductor have internal resistance, so that here we have a angle that is pi. So after that we have to mention the voltage drops, and we have a drops of resistive drop, reactance drops, and the combination of resistive and reactive is nothing but impedance drop. Okay, so that resistive drop can be denoted in this phasor diagram. See here how to draw, means from the point of voltage parallelly we have to draw a line, and this line represents that IARA drop. IARA drop. The line should be drawn parallel for the armature current. And now we have to represent the reactance drop. So that reactance drop will start from the IARA drop and it should be perpendicular to the IARA drop. So draw a perpendicular line for IAXA drop. Now the resultant line is nothing but induced EMF. Induced EMF. And the resultant of IARA drop and IAXA drop is impedance, that is IAZA. So this is a normal basic phasor diagram for lagging. If it is a leading, then the current will be leads the voltage. Okay. So here the first step is first draw a voltage V. After that draw a current with the lagging angle of pi. So this lagging angle of pi is depending upon the load. If it is a resistive load, then it is for unity. So the current will be in phase with the voltage. Okay. If it is here we are considering inductor, so that it is lagging with an angle of pi. If it is a capacitive load, it have a leading power factor. So the current will be lead the voltage. For example purpose, here we consider the inductive, that is lagging. Okay. So After considering of this load, now we have to draw the voltage drops. So one is IaRa drop. This IaRa drop is parallel to the current. After that, next step, we have to represent the reactance drop. That reactance drop is perpendicular to the IaRa drop, and the resultant of this armature voltage drop and the reactance drop is nothing but impedance drop. Okay, the resultant line gives the induced EMF. So this is the basic steps to draw the phasor diagram, right? So now we will discuss the phasor diagrams for a loaded alternator. Okay, so now see here, if you here you can observe the lagging power factor for the loaded alternator. So here we are considering the reference line is current. Previously we taken voltage as the reference line. Now we are taking the reference line is current. Okay, so here if you observe OE line, this OE line is the reference line and it is a lagging. So this current lags the voltage. So here in the upper direction we have a voltage V phase. Okay, and the IRA drop is parallel and IAX is the perpendicular and the resultant is the induced EMF. Okay, so here you can observe the OA is the V phase. Okay, and AB is the IARA and BC is the IAXS and OC is the E phase and AC is the IAZS. So from this phasor diagram, now we have to derive the EMF equation. E phase we have to find. Okay, so now we will see step by step the E phase. Now here we have to consider, we have to take the cos pi at an angle of pi. Okay, so cos pi equals to, so we know cos pi is equal to adjacent side by hypotenuse. Here the adjacent side is, here the adjacent side is OD, and here we are considering the triangle of AOD, the triangle of OAD we are considering. Okay, so here we are consider the OAD triangle, and cos pi is equal to adjacent side by hypotenuse. Here adjacent side is nothing but OD and hypotenuse is the OA. Okay, so by doing of cross multiplication we will get OD is equal to OA cos pi. So here OA is nothing but already we know V phase cos pi. V phase cos pi. For the same angle, now we have to apply the sine. So if you apply the sine, sine pi is equal to opposite side by hypotenuse. Here the opposite side is AD. Here the opposite side is AD and hypotenuse is OA. So in the place of OA, we will substitute the V phase. So it will come, so here OA, sorry, so we have to write the equation for AD equals to OA sin pi. So here OA is V phase sin pi. So now we find the value of OD and the value of AD. These two values we found. Okay, so now we have to consider the triangle of O, C, E and O. Okay, so these triangle we have to consider. Here the triangle we have to consider is O, C, E. For these triangle we have to apply the Pythagoras theorem. So from the Pythagoras theorem we can write the equation is larger side equal to other two sides. Here the larger side is OC. So OC square is equal to OC square is equal to OE square plus CE square. OE square plus CE square. Okay. So here OE means E phase. So we can write here E phase square. Now OE, this OE can be written in written as OD plus DE. If you see here, this is the OE line. In this OE line, OD is the one part and D is the another part. So OE can be written in the form of OD plus DE. So here we can write OD plus DE square plus. Now here another line is CE. The CE also can be written as two parts. One is BE, another one is BC. Okay. So here we can write BE plus BC. Okay. Now we know the values of this OD, DE, BE and the BC. Okay. Now substitute here. Okay. So E phase square equals to, now OD. OD is V phase cos pi. Okay. Right here V phase cos pi. Next DE. So here if you observe in the phasor diagram, here DE and AB are same. Okay, the distance of AB line and the distance of DE line both are same. So here AB is represented as IARA. So DE is also same as IARA, same as AB, IARA. So here we can write IARA, it is whole square plus now BE. Okay, so if you see here BE is equals to AD. B is equal to AD. Okay, so when B is equal to AD, we know the value of AD is V phase sin pi. Okay, so we know already AD is equal to BE. So we find the AD value as V phase sin pi. So in the place of BE, we can write V phase sin pi. So it is V phase sin pi plus BC value. So the BC value is IAXS. IAXS square. Okay. So E phase equals to under root of V phase cos pi plus IA RA square plus V phase sin pi plus IA XS whole square. So this is the EMF equation for lagging power factor under loaded condition for the alternator. Okay, so this is one type of load power factor, and we have another two, that is one is leading power factor and unity power factor. Now we will go for the leading power factor. Let me see. So see here the phasor diagram. Here again we considered the reference is IA. So here IA value is OE line is the IA, okay, reference line. And here when we take an IA is the reference, the voltage should be lead. So here we have a voltage, that is OA line. This is the OA line. Okay. And the IA area should be parallel. So here AB is the parallel to IA. And IAX should be draw perpendicular. Here we written perpendicular. And the resultant is E phase. The resultant is the E phase. Okay. And the resultant of IARA and IAX will give the impedance drop. So that is this line. AC is the line, IA ZS. Okay. So from this phasor diagram, again we will find the EMF equation for loaded alternator. Okay. So here we are considering OAD. Okay. So here this is the O and it is the A and it is the D. Okay. So here the triangle we are considering, O, A and the D. These triangle we are considering. Okay. So from this triangle we considered, okay, we taken cos pi. Okay, we taken cos pi. So cos pi equal to again adjacent side by hypotenuse. Here the adjacent side is OD. Here the adjacent side is OD and hypotenuse is the OA. So by substituting that value, we will get the OD is equal to V phase cos pi. V phase cos pi. Okay. Next, we have to find the AD or BE value. AD is equal to BE. Why? Because both the lines are in parallel. So both are same. So now we have to find BE value. Okay. Sorry, AD value. So here we have a AD. So apply the sin pi. So when we apply the sin pi is equal to opposite side by hypotenuse. So here opposite side is AD, hypotenuse is the V phase. By simplifying it, we get AD is equal to V phase sin pi. Okay, so we got it. And DE value, AB is equal to DE. Here AB line and the DE line both are same. So here AB value is equal to DE value. So here D equal to IARA and AB is equal to also IARA. Okay, these are the values we found. Now we will go to derive the E phase. Okay. So here now consider the triangle OCE. The triangle OCE. This triangle we considered. OCE triangle we considered. So for this OCE triangle, now we are writing the Pythagoras theorem equation. Okay. So from the Pythagoras equation, we can write the higher side is equal to other two sides. OC square is equal to OE square plus EC square. Okay. So here OC is nothing but we can write E phase square equal to, okay. Now OE. So here this is the OE. OE can be written as OD and DE. So these 2 points are considered as OE. Okay. So in the place of OE, I will write OD plus DE. Okay. Place. Now EC. So this one we have to know, but we don't know about the EC. Now we have to find the EC. Okay. So to find the EC, see here the BE line. Already we know the BE line. Okay. So BE, we know the BE and we know the BC. In the total line BE, if you subtract the BC, then you will get the CE. Okay. So by doing of that, so EC can be written as the total line BE minus. So in the total line, if you minus the BC, then you will get EC. Okay. This is square. Now E phase square equals to what is OD? OD is nothing but V phase cos pi. V phase cos pi plus what is D? We know D is equal to IARA square plus what is B? B is nothing but V phase sin pi. V phase sin pi. Okay. Now minus BC. What is the BC? BC is equal to IAXS square. Okay. So now we can write the equation for E phase equal to under root of V phase cos pi plus IARA whole square plus V phase sin pi minus IAXS whole square. So here if you observe here both the equations, there is a small one change is there for lagging and the leading. For leading, here we observe the negative. Okay. And in the lagging, we observe it is plus. It is the plus. For lagging, here the sign will be plus. For the leading, here the sign will be negative. So these are the 2 derivations for lagging and the leading. The next one is unity power factor. Next one is the unity power factor. So if you observe, here we take in the current IA as a reference. So we know in the unity power factor, the voltage or current both are in phase. So here the voltage also in phase. Okay. So current and voltage are in phase. So the IARA drop also in phase. For this IARA drop, we have to draw a perpendicular line, that is IAXS, the reactance drop. So the resultant is E phase. And the 2 drops resultant is impedance, that is AC IA ZS. Okay. So this is the unity power factor phasor diagram. Okay. Now here also we will derive the EMF equation. So consider the triangle OBC. Here we have OB and here C, OBC triangle. So from this OBC triangle, we are applying the Pythagoras theorem. Okay. So OC square, OB square plus BC square. Okay, so this OB can be written as OA plus AB. So OA plus AB, and BC direct line we have. So here OA value is V phase. So we have to write V phase, and AB value we have IARA. Substitute here IARA, and the BC is IAXS. So under root of V5 plus IARA plus IAXS whole square. So this is the unity power factor for loaded alternators. So for loaded alternators, we seen the different and various power factors: lagging power factor for inductive load types, leading power factor for capacitive load types, and the unity power factor for resistive type. So these are very important for alternators on different loads of the phasor diagrams. Okay, so thank you for this class. Next class we will discuss next topic. Thank you.